Welcome back, guys. We are back with a very interesting problem on dynamic programming, and this is a problem that's slightly asked in a lot of companies, and this is a DP problem, and it's a DP Max problem, and it's so you can see it's a medium problem, and it's not really hard if you go in that range. So what is this particular problem basically telling you? So it's like we have a binary matrix, okay, which has size n cross m. So if you have a binary matrix, say for example, which is size n cross m, what basically you're going to do next? Will you work with this matrix? We are going to find the maximum length of the side of a square of submatrix with all ones. Okay, so this is a kind of challenging problem, and how we are going to tackle this problem? So it's like, if you see what is n equals to 6 and m. So if you see it has 6 rows and 5 columns. Okay, 1 2 3 4 5. It has 5 columns, and these are columns, okay, and it has, say, 6 rows. It has, say, 6 rows, okay. So if I see the 6 rows, I have to count the total number of maximum length of a side of a submatrix with all ones. Okay, maximum length of a side of a submatrix with all. You're saying the maximum length of side of a side matrix is all. Okay, so what is a submatrix? What is a square-shaped submatrix? So any matrix which is just one, we are going to declare it as a square-shaped submatrix. So let's count the total number of submatrices over here. Okay, so if I count the total number of submatrices, individual ones. First, I'm going to do matrix of size 1. Matrix of size 1. In size 1, how many matrices I'm getting? I'm getting 1, 2, I'm getting 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there is total 16 submatrices which has size equals to 1. Now my target is I am going to return the maximum length. So now I'm going to go with size 1 with size 2. Okay, matrices of size 2. So which matrices can be a square matrix and which has a size equals to 2? Okay, which has size equals to 2. Let me just quickly remove the calculations. Yeah. So over here, if I'm going to find out such type of square matrices with size equals to 2, what is a square matrix? Square matrix is having rows and columns equal. So if I see rows and columns equal, how many are there? So this is a matrix 1, okay. This is 2, okay. This is a matrix of size 3, total 3. If I take this one into account, I'm having a 4. If I'm having this one into account, I'm having a 5. Okay, so I guess I have done total. There are 5. I've calculated all the possible possibilities of the submatrices. The total equals to 5. Okay, so next what I can do is I have to check what if the size is 3. Okay, so that's the maximum possible iteration I have to work on, right? So if my matrix of 1 with size equals to 3, I have to find a submatrix which has length and breadth equals to 3, means 3 rows and columns. What is that maximum length? Okay, so if such matrix exists or not, first I have to check that. Okay, if such type of matrix is existent or not existent in nature. So if I see there's only one such matrix, which has size equals to 3, so the answer is 1. So the total count of possible submatrices. So here is an interesting question. This question can be also given as, what is the total count of possible submatrices? So if you have a total count of submatrices, square-shaped submatrices, okay, so you will get the answer as 21 and 22. So there's a lot of submatrices present. So how we are going to apply our knowledge into this particular problem? Okay, so when you're solving this, the first thing is like this: oh, I don't know DP, right? So if the interviewer asks you this question, how we are going to solve this, you're probably going to use a brute force. So brute force is basically like, oh, if I'm going to start from one particular cell, I'm going to start from one particular cell, and I'm going to go to the diagonal cell, and I'm going to check if the square of such cell exists. Then I'm going to the diagonal cell, and again I'm going to use 2 or 3 loops to go to the diagonal and go to the diagonal, and you don't know how big is your matrix n cross m, right? So this is going to take an increasing large amount of time complexity. So how we can solve this? We can use a recursion as well. But in case of a recursion also, we have seen that there is a particular point where the time limit will get exceeded. So what is the best technique to solve this is using a DP table. Using a DP table, we can solve this and using a formula which I'm going to discuss today, we're going to solve this problem in no time. Okay. So let's just start solving. Let's just start taking some examples and then go with the problem. Okay. So first example which we are going to do is we are going to take a submatrix. Okay. We are going to take some submatrices and we are going to learn the possible k count of the total number of submatrices. Before we are going to find what is the maximum length, we are going to also check the total count of submatrices. Okay. So suppose this is a submatrices 1 1 0 1 1 0. So what is the total count of one side submatrices? There is a total count of 7. If you see the total count, this is 1 2 3 4 5 6. Okay, 3 4 5 6. Okay, and our submatrix over here 1 2 3 4 5. Yeah, total count of submatrices. If I see a square shaped submatrix of size 1 itself plus 1 is total count is 7. Okay, so in this case it is 6. Yeah, 4 5 6. Yeah. So if I say, for example, I'm going to check a square matrix, okay, of say for example I'm going to take another example of square matrix. So this is my square matrix. Okay, in the square matrix I'm going to take some values. So probably 4 columns and some couple of rows. Okay, so I'm going to take 0 1 1 and 1. I'm going to take all ones over here, and I'm going to also take 0 1 1 and 1. So total count of one-sized submatrices is 1 2 3 4 5 6 7 8 9 10. Okay, total count is 10. Now the total count of two-sized submatrices, okay, so I will write it over here as two-sized submatrices. So a two-sized submatrices is the one which has rows and columns as 2. So this is 1 2 3 4. Okay, so I guess there are a total of 4. Okay, and a three-side submatrix. A three-side submatrix is this particular matrix which has 3 rows and columns. So I can write it like a three-side submatrix is only 1. So if the total count they ask me, my total count is 15. Okay, but there is another technique which I'm going to use. Till how long you are going to check this? There must be some shortcut, right? So I'm going to tell you about the shortcut formula. So the formula which we are going to use is we are going to take the minimum of the 3 sides, okay, of a diagonal of the top element and the left element, and then we are going to solve it using a DP table. So say for example we will have 2 matrices. Okay, we will have 2 matrices. The first is the input matrix. Okay, the input matrix of the, so this is the input matrix. This is the input matrix. Okay, yeah, this is the input matrix. I'm going to fill the matrix with 1 1 1 1 and 1. Okay, now I'm going to convert it into a DP table. Now I'm going to construct a DP table which is going to help me get the maximum length, which is going to store the length basically. Okay, which is going to store the length. So in the DP table, one thing we have to make sure that the table should always be of the same size of the matrix given. You cannot construct a DP table of greater size or smaller size. The DP table should always be of the same size. So I'm going to first quickly fill the values inside the table. Remember, whenever you're putting the values, the border values has to be the similar values. So the border values, you just put it like this. Okay, now for finding this particular value, what I'm going to do is I'm going to do a minimum of this and this plus 1. Okay, this is my formula. So what I can see is the minimum of all the 3 is 1 and plus 1 is 2. Okay, so if suppose there is a matrix like this, then what will be the length of this particular matrix? what will be the side of the particular matrix? The side is obviously 2. It's 1 plus 1. We say there is 2 rows, 2 columns. That's the reason we are getting 2 over here. Okay. So similarly, what we are going to check in this particular case, we are going to take the minimum of all 3 values, 1, 2, and 3 of the top cell of the diagonal cell and the left cell. The three values, okay, you can write like this, and this, okay. The 3 values is minimum is 1 plus 1 is 2, okay. Now let's come to this particular problem. So if you come to this particular problem, over here you have to also again take the minimum of the 2 cells, which is 1 and 2 and plus 1, so this will also become 2. But see, for example, now you're over here, okay, now you're over here. How you're going to find the length of the thing which has of the size, okay. Now if you see carefully, I am reaching the cornermost cell. The cornermost cell has a coordinate as n comma m. Why n comma m? Because we have to maximize the capacity of the n comma n, where n and m is the length of the cell. So this is the last point, which is basically nothing but 3 comma 3 if it's a 1 mixed indexing, or 2 comma 2 if it's a 0 mixed index, okay. So at the 2 comma 2 I have 1. So if I take the formula how to find the length of the, what is the largest matrix I can get? This entire matrix is the largest matrix because it has 3 rows and 3 columns, okay, 3 columns. So basically what I'm getting is my side length n equals to 3. This is my largest length possible. But if I apply my formula, am I getting the largest length? The answer is the minimum of 2, 2 and 2 is 2 plus 1 is 3. So yeah, this formula works. So in no time you can literally find the largest length present in a submatrix of square. So what I'm going to write it over here is the most genuine formula which you're going to use while filling the table. Okay, so while filling the table, you're going to use dp of I equals to minimum of dp of I minus 1 and j. If somebody asks me what are this, I'm going to explain. And the diagonal elements is dp of I minus 1 and j minus 1. Okay. Similarly, the leftmost element is dp of I and dp of j minus 1. Okay. And lastly, a plus 1. This is the formula. So I'm going to quickly write it over here, the rows and the columns. So this is the top cell, this is the diagonal, and this is the previous cell. So if you see carefully, this is my top, this is my previous cell from where I was. So for previous, you can see I'm taking a j minus 1, means I'm taking the column minus 1. This is the previous column. But my index, my particular row will be fixed. If you see in this case, the row is fixed. Okay. If you see in this case, the column is fixed, because in this particular column, I am where I am, but right on the previous column, right on the previous row. So this is a variable row and the column is fixed. In case of a diagonal, it is just the previous column, previous row, and the top value. So I'm just using that's the reason I'm using I minus 1 and j minus 1 over here. Okay. So over here is the column is fixed, and in this case the row is fixed. Okay. So that's how you can get the count of the number of square of submatrices. And now we are going to analyze this particular problem. Okay. So you can see, first I'm checking if my n and m equals to 0. Then I'm returning 0. Means this length is 0. Means there is a matrix which has no length. So I'm going to return the matrix length as 0. Then I'm going to create a DP table which has n and m as the size of the DP table. Now I'm going to initialize the DP table. And by initializing, you can see I have traversed it through rows and columns. If the cell is on the border, it can only form a square of side 1. So in the case of border cells, I have initialized all the squares as the side length 1. Okay. After that, whenever I'm encountering a cell value of 1, I'm going to use the formula which I already told you. Else, I'm going to fill the cells with 0. Lastly, we are going to calculate the maximum length as the previous length obtained and the current length. Taking the max value, we can obtain the maximum side length. So this is an easy problem on DP, and we are going to solve this problem, and we are going to see if we can solve this problem without taking help from the solution and stuff. Okay. So this is the largest square problem. And what I'm going to quickly do is, I'm going to remove this, okay, and try solving this. So my first test case is whether my size is equals to 0, and Should I take an AND operator or an OR operator? I'm going to just quickly check. We have to take a OR operator. Okay, so OR m is equals to 0. Then what I'm going to return is 0. Okay, this is my first test case. After this, what I can do is I can initialize a DP table. I can initialize a DP table equals to new int. I can take the size of the DP table as the same size of the rows and columns of the table. Okay, now I'm going to traverse to the table and fill the table. I less than n plus plus. Okay, j equals to 0, j less than m, j plus plus. Okay, once this is done, what I'm going to check is my base cases. So if my matrix, if the I is equals to 0 or j is equals to 0, what I'm going to set is dp of I and j is same as matrix of I and j. This is nothing but I'm filling the border cells as 1. Okay, then in the else if condition, what else if condition I'm going to pass? Okay, else if I get such a type of cell where the values are 1, because a square can only be formed if the values are 1. Okay, so in this case a square can only be formed if the values are 1. So over here I'm going to write matrix of I and j is equals to 1. Okay, what I'm going to do is I'm going to fill the DP table. Okay, I'm going to fill the DP table as dp of I and j is equals to mat.min dp of, as I told you, I have to take the top value. Okay, so in case taking my top value dp of I minus 1, I'll be on the same column, so I don't have to change the value of j. For diagonal, I have to move both the pointers, I minus 1 and j minus 1. Okay, so for diagonal I have done already. What is this? Oh, don't give a. Sometimes this is irritating because they're giving advertises. So if you see dpi minus j and j, and the last cell probably will be I and j minus 1. J minus 1. Yeah. So I've encountered all the cells over here. Yeah. In this case, there will be an else part. So in the else part, I'm just going to write dp of, I'm going to fill the cells with 0 equals to 0, and once my traversing of the entire process is complete, I can write simply return what I have to return, the length, right? So I have to return the maximum side length. So maximum side length, where can I compute? Yeah, so I can compute over here a maximum side length. So max equals to mat.max of max and side length of, say, dpi and j, side length of dpi and j. So where can I get the max value? I can just initialize the max value somewhere over here, and return the max value, So over here, most probably I'm completing the function over here. Yeah, I'm going to quickly iterate. You see there's an error, mat.min. I have to give a +1 as well. Okay, there are 3 values. Let me just check what I did over here. Yeah, I did 3 values. What is the problem? Again, I have to use a mat.min for the last 2 values. Okay. This is a kind of boring thing. I have to use again a mat.min. These are, yeah, some Java fundamentals. Yeah, so it is working. That's a good sign. Oh, 0 test cases. Index -1. Let me just check. 0 0 nmm return dp nm max square. Where did I mess up? maximum side length 0, return 0, ing equals to mat of ing. Honestly, why did I mess up? Did a maximum side length of, I'm going to just quickly project it over here and check where I messed up. So if I check n equals to 0, m return 0, okay. If the max is 0, okay, we are traversing m if ing equals to mat of ing. Else if is also done. So else if is also done. A equals to mat.min of dpij, comma mat.min of dp of I minus 1, excuse me, dp of I minus 1 j minus 1 and I and j minus 1. Okay, so I guess I messed up over here. dp of I minus 1, dp of, sorry, I minus 1, j minus 1, yeah. So if you see, this bracket gets closed over here. And is there a main bracket as well? Yeah. So if you take the total minimum, yeah. So I and j minus 1, and dp of the diagonal plus 1. Okay. Else part is also okay. Maximum side length. Let's submit. We are using the compiler too much, that's why it's lagging a little bit. But it's okay. We have successfully completed today's problem statement as well. So we are looking forward to solve more problems. Thank you.